Hey everybody, your Friendly Math Tutor here with our AP Calculus BC practice test. So in this video, we are going to attack Part A, which is 30 multiple choice non-calculator questions. So let us start with number one. So we have a function that is above the x-axis, continuous, and we want to know what must be true. So we start with the fact that it says that it's differentiable. Well, if you think of something like a corner, you could have a corner at 4 where it's continuous but not differentiable. So it doesn't have to be differentiable. And B is saying the same thing. We have to understand they give you things in different ways. And this is really just the definition of the derivative at a specific point. So this too would be giving us the derivative evaluated at 4. And that value would represent, same thing, slope of the tangent line. But this doesn't have to exist because, like I said, it wouldn't exist if it were at a corner. So that answer is wrong. Now, this is the integral from 0 to 4. The integral is the area under the curve and above the x-axis, or above the curve and below the x-axis if it is below the x-axis, and that would be a negative value. But this says that it's always above the x-axis, and this is saying that it's less than 0. So that's a contradiction, so that one's wrong. And obviously this is the answer, but this is because in order for something to be continuous, the limit has to exist, and in addition to that, f of that value, so in this case f of 4, would have to be the same answer. But we don't even need that. It's not even saying that much. We know that that's true for it to be continuous, but at the very least, we know if it's continuous, the limit definitely exists. So in that one, we have answer choice D. All right, on to number 2. So when you see a limit as x approaches a numerical value, the first thing you want to do is substitute, direct substitution. So you throw in 2 and you get the sign of 0, which is 0. Then you put 2 here, and you get 2e to the 0 minus 2, which is 2 minus 2, which is also 0. So typically, this tells us that we want to do L'Hopital's rule. So L'Hopital's rule works like this. The limit as x approaches 2, and I'm going to take the derivative of the numerator, which is cosine of x minus 2, over the derivative of the denominator, which is 2e to the x minus 2 minus 0, because the derivative of minus 2 is 0. So now I do direct substitution again. I throw in 2 here, but this time the cosine of 0 is 1. And if I plug in 2 here, I get 2e to the 0, which is 2. So now I actually get an answer, and that is the answer. So we get answer choice B. All right, let's move on to number 2. So we have derivative, second derivative in parametric. So the way that looks is this. You take the derivative with respect to x of the first derivative. This is just notationally what it looks like. This is where this comes from. And dy dx we're going to find using these, but that is going to be in terms of t. So we really have to do our second derivative in terms of t. So what that looks like notationally is we're going to take this d and this dx and divide them both by dt. So I get d dt over dx dt. All right, just algebraically we're allowed to do that, but the d dt I'm going to apply to this. So what this looks like in application or in practicality is I'm going to take the derivative of whatever dy dx is with respect to t, and then I'm just going to divide it by whatever dx dt is. And that is going to give me the second derivative. So let's look at dy dx first. So dy dx is going to be ln t divided by sine 2 to the t. All right, because dy dt divided by dx dt will give me dy dx. Now what I have to do is this. I have to do d dt of both sides, which I'm doing the quotient rule. So I first do derivative of the numerator, which is 1 over t, times the original denominator, so sine 2 to the t, minus, keep the numerator the same, and then multiply by the derivative of the denominator. The derivative of sine is cosine. 2 to the t stays the same. Then I multiply by the derivative of 2 to the t, which is, 2 to the t ln 2. I'll throw parentheses around here just to kind of separate everything. And then all over the original denominator squared. All right. Now, all of this has to be divided by dx dt, which is sine 2 to the t. And I'm going to stop here. And then hopefully we're in AP Calc BC class. We don't want to have to keep writing out our work. We want to be able to figure out the answer because it's multiple choice which one it is. So hopefully we know that when we do this divided by this, it's like we're multiplying by the reciprocal. This ends up in the denominator with this. So we should have a sine 2 to the t cubed. So that gets rid of these. And then in the numerator, it just should match what I have here. And that ends up being d, because I have sine 2 to the t over t. And then I have right here, I have an ln 2, I have a 2 to the t, I have a cosine 2 to the t, and I have an ln t. In a different order, but we end up with the same thing. So the answer ends up being D. All right, let's keep going. So here we are at number 4, and we have an improper integral. The way we do an improper integral is we take the limit as, I don't know, let's say b goes to infinity of the integral from 1 to b, all right? But actually, you know what? I usually use b, but I'm going to use x in this one because they're putting an x here. So we're really doing the limit as x goes to infinity of the integral from 1 to x of f of t dt. Okay? But they're telling us that this is this. So then I have 5x squared over root 9x to the 4th plus 12x plus 7. And the way I want to evaluate this limit is I am going to divide this numerator by x squared, but I'm going to divide the denominator by root x to the 4th. So first notice that sorry, I'm rewriting this. So just notice that root x to the 4th is x squared, so I'm dividing the numerator and denominator by the same thing. And then that allows me to simplify this, so that gives me 5. And it also lets this x to the 4th like infiltrate itself into the square root because I'm doing a square root divided by a square root. So I get one big square root, and 9x to the 4th over x to the 4th is 9. And 12x over x to the 4th is 12 over x cubed. And I have this plus 7 that we can't forget about. So then when I take the limit as x goes to infinity, all the constants are themselves, and something like this, 12 over infinity, goes to 0. So I just end up with 5 over root 9 plus 7. Again, this is where I would stop. This is 5 thirds plus 7, which is 26 thirds, because it's 21 thirds plus 5 thirds. And that's it, yeah. So again, get into the habit of stopping the problem a little bit early on these MCQs, just algebraically, once you've done all the calculus, and then figure out the answer from there without having to write it all out and, you know, spend a couple extra seconds, but per problem that can add up. All right, so now we take a look at number 5. So which of the following series are absolutely convergent? So I'm going to dive right in here on the first one. If it's absolutely convergent, then what I'm really looking at is the series n equals 2 to infinity of 1 over 3n plus 1 factorial, simply because it's the absolute value of it should converge. So the absolute value of it is going to get rid of the every other term being negative, so I can ignore the negative 1. And what I'm going to do for this is the ratio test. So the ratio test tells me I'm going to do the limit as n goes to infinity of a sub n plus 1. So that is 1 over, if I replace this with an n plus 1, again, I'm going to try to do the algebra over here. This is 3n plus 3 plus 1, so that's 3n plus 4 factorial. If Then I'm going to divide it by a sub n, which is like multiplying by the reciprocal. So that's 3n plus 1 factorial over 1. And then this is the limit as n goes to infinity of, well, what happens down here is I can rewrite this as 3n plus 4, 3n plus 3, 3n plus 2. Remember, factorials just keep multiplying by the one below it. Then I get 3n plus 1 factorial, which cancels with this. So I end up with that. This limit is clearly 0. Hopefully we can see it's 1 over infinity, or 1 over an infinite limit. And that means that since that's less than 1, by the ratio test, this converges. So which is a series converges absolutely? That one does. So this is out and this is out. So this means I really only have to check 3. So if I jump to 3, I'm doing the series from 0 to infinity of 5 over 2n plus 5, because again I want it to converge absolutely, so I just basically ignore the negative 1. Here I'm going to do the limit comparison test. So I'm going to call this a sub n, and I'm going to call b sub n 1 over n. And know that the summation of b sub n diverges, my bad. This is a harmonic series or a p series with p equal to 1. That clearly diverges. So what I do is the limit as n goes to infinity of a sub n over b sub n, that's 5 over 2n plus 5, over b sub n is multiplying by the reciprocal. So when I multiply by n over 1, I get an n up here. This limit equals 5 halves. So this is how the limit comparison test works. If the limit of a sub n over b sub n is equal to a positive numerical value, then a sub n and b sub n do the same thing. Since b sub n, the summation of b sub n, diverges, then the summation of a sub n is also going to diverge. So this one does not converge. So it must be a1 only, because this does not converge. And we could check this one. We don't need to. But just to talk about the concept, this one you would just simplify to a p series, and you would also see that it easily diverges. So the answer is A. All right, let's keep it moving. So we take a look at number 6. And what we have here is we have to understand the limit definition. So the limit definition of an integral is the limit as n goes to infinity, the summation from k equals 1 to n, of f of c sub k, which is a plus k delta x times delta x. This is the height of each rectangle. This is the width of each rectangle. This is the summation of all the rectangles. And this is saying make there be an infinite number of rectangles. And that's where the exact area lies. So this is equal to the integral from a to b of f of x dx. So what we have to do is locate a, locate b, and locate f of x. And then this one has a little extra thing in it. So a is going to be here. So a is clearly 3. So this one's gone. Now delta x is going to be here. So if I ignore the k, so right now I know a is 3. Delta x is going to be this part, the part that's being multiplied by k. So that means delta x is 4 over n. And we should also know that delta x is b minus a over n. Well, if a is 3, then b must be 7, because 7 minus 3 would give us 4. So 7 is here. That doesn't really help me. Every answer has that. Now the function itself is going to be this whole part. The 3 plus 4k over n is our c sub k here. That's being plugged into a square root function. So I have root x dx, all right? And it seems like, oh, the answer should be D. But be careful. I kind of wrote over it, but this part is 1 over n. But delta x is supposed to be 4 over n. So that 1 over n must have got multiplied by a 1/4 to get 1 over n. So that's why there's a 1/4 out here, and it is actually C. This is a very tricky problem, because usually once you locate A, then delta x, then B, then the function, you're usually done. But this one has like an added, kind of gem in it here, that the delta x that's here has to match the delta x that's here because it's the same thing. And the only way that could change is if it were multiplied by some like factor or constant that was then, moved in front, as we typically do with constants or coefficients in integrals. So that one's very, very tricky. All right. Now we move on to number 7. And in number 7, what we're going to do is first just go right to, we're finding the derivative of h of x. So this is chain rule. That is the derivative of the outside function times, with the inside function remaining unchanged, times the derivative of the inside function. And if I want h prime of 1, I'm going to find f prime of g of 1 times g prime of 1. And then I'm going to use the information given. So if I want g of 1, that I'm just going to use this. So g of 1 is 1 plus 1 minus 1, which is 1. So I have f prime of 1. And then I have times g prime of 1. Well, if I want g prime of 1, I'm just going to take the derivative of this. And I'm going to do 2x plus 1. So g prime of 1 is 3. Now I need f prime of 1. Well, I go to the graph. 1 is here. If I want the derivative of that, I need the slope of this line. So it might be hard for you to see, but this point is 1, 2, 3, comma 4. And this point down here is 0, comma negative 1. So the slope of that line is f prime of 1. All right? Well, the slope of that line is rise over run. So going from negative 1 to 4, I'm going up 5. And then I'm running 3 because I'm going from 0 to 3. So the slope is 5 over 3 times 3 gives me 5. So the answer to the problem is 5, which is A. All right, let's keep this moving, and we take a look at number 8. We have a pretty straightforward problem here. It's just multiple chain rule. So if I want to do the derivative, start with the outer function. The derivative of tangent is secant squared, and everything inside remains the same. Now my next most inner function, or outer function, however you want to look at it, but if I go one layer deeper, I'm at ln. The derivative of ln x is 1 over x, but in this case it's the ln of something, so the derivative is 1 over that something. Now I make it to my final layer, and I got to do the derivative of 5x, which is 5. All right, so these 5's cancel, and I'm basically left with this over x. Again, I don't want to write anymore. I just want to go and search and find that same answer. That might be written a little bit of a different way than I have it, but I want to waste time writing. So the answer is C. All right, let's move on to number 9. So here we have a limit of a composite function. So the way you want to look at this is when you think about how a composite function works, like when you learned it maybe in Algebra 1, is that you have an input that goes into the inside function, and then that gives you an output, and then output becomes the input to the outside function, and then you finally get your final output. So as x, what we want to do is look at the inside function first. We want to say, all right, well, the limit as x goes to 2 of the inside function is from the left and from the right is going to meet up at this hole, which is 3. So the inside function, as x gets closer to 2, the inside function outputs are getting closer to 3. So then what we want to do is we want to go to the outside function and say, okay, well, what's happening when that gets closer to 3? Because the outputs from the inside function become the inputs for the inside function. So as x gets closer to 3 there from both ends, then, because this is going to be approaching 3 from both ends, then that is getting closer to 0. So the overall answer is 0. All right. Now we got a Taylor series, and we're looking at the alternating series error bound used to approximate f of 1/3. So we would say that the error in the alternating series error bound, the way that it works is the error is at most the absolute value of the first unused term of where we cut it off. So these polynomials, these Taylor polynomials, are just a chunk of an infinite series, and we're going to chop them off, and then the first unused term is what the error bound is going to be. It can't be more than whatever that term is evaluated at our specific x value. So if we look here, the way I'm going to get a 9th degree polynomial is it's going to be when n equals 3. Because when I plug in n equals 3, I get x to the 9th. So then that means when I go, I'm basically chopping it off. I'm doing like n equals 1, n equals 2. And they're being added together. And then I'm stopping at n equals 3. So then n equals 4, whatever that is in the series, is going to be my error bound, or my error term, we can call it. So what I get is when I plug in 4, well, -1 to the 6th is +1. When I plug in 4 here, I'm going to get 3 times 4, which is 12 plus 1, so that's 13 factorial. And then I'm going to get my x is 1/3. So let me give myself some room here so we can really see what's going on. Whoops. So now this x right here is really 1/3, and that's being raised to the 12th because it's 3n and n is 4. So now what I'm going to do is find my answer. All right. So I should have a 13 factorial on the bottom, and then I should have 1/3 to the 12th, which is 1 to the 12th is 1, and then I should have 3 to the 12th. So I'm going to have that. So the answer is D. All right. So wherever you stop, the next n, the next term, represents your error term, is the error bound essentially for any alternating series. All right, not to be confused with the Lagrange error bound, which I'm sure we'll see at some point during this test. All right, on we go. So this one I want to go over more conceptually, as opposed, there's a formula that you could just memorize, but I like to do these more conceptually. It helps me just attack them without having to just like blindly use a formula. So what we have is we have an f function and a g function, and we have points that are on that function. And the corresponding points on that function are just flipped because they're inverses of each other. That's just what an inverse is. It flips all the points. So what I have is I want the value, and then, my bad, at each point I have a g prime and then I have an f prime that represents the slope of the tangent line at that input for that function. So I start here. G prime of 1, well, that is this, okay? So when I find G prime of 1, that's the slope of the tangent line at 1 on the G function. But I don't really know anything about the G function. I have no information about it up here. But what I do know is that if 1 is the input on the G function, then it's the output on the f function because they're inverses of each other. Then I go here and I say, okay, well, the f function has an output of 1 here when its input is 2. So this is how I can look at it. The point 2,1 becomes the point 1,2. And then here, the slope at this is just f prime of 2, because that's the input, and that's 4. So I really only need this column. Everything else is just to mess with you. Well, then what happens is, if the inverse graph just flips all the x's and y's, then the slope just flips, right? The rise over the run kind of becomes the old run over the rise. So that gives me 1/4, and that's the answer. All right, so you just got to figure out that this is the output to the f function. The input to the f function is this. The derivative of that is here, and then you take the reciprocal of it because that's the relationship between corresponding points on inverse functions. Their slopes are reciprocals of each other. Not to be confused with perpendicular or normal lines where it would be the opposite reciprocal. This is just the reciprocal. All right, on to number 12. So what I'm going to do is two things. I am going to split this up into two different integrals. These should each have a dx. All right, So this first integral, I'm going to use u substitution. I'm going to make u the entire bottom. du is e to the x plus 2 dx, which works out perfectly because I have an e to the x plus 2 dx there. Let me remember that that's subtraction. And I have my u on the bottom. So I have the integral of du over u. And then I want to change the limits of integration. So when I substitute in 0 here, I get 1 plus 0, so that becomes 1. And when I sub in 4 here, I get e to the 4th plus 8. And then I'm just going to do this one. So this becomes the antiderivative of 1 over u is the ln of u. It's really the absolute value, but it's not going to matter because these are positive. And then it's evaluated from 1 to e to the 4th plus 8. And that means I do fundamental theorem of calculus. So the ln of e to the 4th plus 8 minus the ln of 1, but hopefully we know the ln of 1 is 0. So I just get that. Then I go and I do this one. This one is just the antiderivative of 3x is 3x squared over 2, evaluated from 0 to 4. And that one, if I plug in 4, I get 48 over 2, which is 24. And then if I plug in 0, I get 0. And then let's remember that I'm subtracting them. So I'm doing this one minus this one, and that is answer choice C. All right. Let's keep this moving and move on to number 13. So we got a function, and we want to find a point of inflection. What we have to have is very general principles here. Like, anytime I want to find a point of inflection, I want to find the second derivative because or I want to be looking at the second derivative graph or thinking about what the second derivative is doing, right? Depending on the given information. But if I'm given a function and I want to know a point of inflection is when the second derivative changes signs or the original changes concavity. But the second derivative is the sign of the second derivative is the thing that tells me when the original function is concave up or concave down. Okay, so what I'm going to do is I'm going to find the second derivative. Well, the first derivative is the fundamental theorem of calculus part 2, which is just the derivative of an integral kind of cancels out, and all these t's become x's. So I get 54x squared minus 18x minus 8, and then the second derivative is just 108x minus 18. I want to set that equal to 0. That should be 108x equals 18. Whoops. And then x is 18 over 108, which is 1/6. And then I should do this because it's obviously not these, but it could be non-existent if I don't get a sign change on the second derivative. But I clearly do because when I plug in like 0, I get a negative, and when I plug in 1, I get a positive. So it should be easy to see. Maybe you don't even need to write it out, but just check that. Just because you have a 0 of the second derivative does not mean that it's a point of inflection. Two things have to be true, actually. It has to change signs, and it also can't be a vertical asymptote, which this one we don't have to worry about because we're just polynomials all throughout. So the answer is A. So if you just get the 1/6 in circle A, you kind of get lucky. Just make sure you're doing that extra thought. Two real things. Was it undefined on the original function? And if so, it's not going to be a point of inflection because it wouldn't even be a point. And more importantly, make sure it does change signs. Okay, which of the following must be true? So is 3 a critical point? Well, definitely, because the derivative at 3 is equal to 0. But is 0 the actual output of it? And to look at that, if we look at the limit as x approaches 3 of f of x over 2x minus 6, for that to also equal 0, so I'm going to just ignore this derivative right now. Well, for that to be defined, then when I sub in 3, I get f of 3 over 0. Well, then f of 3 has to be 0. We need to get 0 over 0 for there to actually end up being an answer. Because if you get non-zero over 0, you would have a vertical asymptote, and you would therefore have an answer of either infinity or negative infinity or does not exist, and not get a numerical value like 0. So f of 3 also has to be 0. So it is a critical point. F prime of 3 is 0, and the output of 3 is also 0. So 1 is true. It has a local maximum. In order to know that it has a local maximum, we would have to know that the derivative changes from positive to negative, which we just don't have any information about that. So that I'm going to get rid of. So it's not this one. But now I have to check 3. Well, f of x is continuous at x equals 3. Well, what ends up happening is if it's differentiable, the derivative is certainly equal to a value, it's automatically continuous. So it ends up being C. All right, so be careful with that one. We saw earlier, just because something was continuous didn't mean it had to be differentiable, but the converse is true. If it's differentiable, then it is definitely continuous. All right. On to Euler's method. So the way Euler's method works is, first of all, we're going to know that x1 here equals 3 because the step size is 3, all right? And then we are in search of f of x sub 1, okay? That's what we want to put here. So what we're going to do is we are going to use kind of the way this works is if I want to find f of x sub 1, that's going to be equal to f of x sub 0 plus our step size, so delta x times our slope, so f prime of x sub 0. Okay, so that's just the layout of Euler's method. So f of x sub 1 is going to be, well, f of x sub 0. So when I sub in 0, I get 1. And then when I do delta x is when I plug in the point to the differential equation. Well, when I plug in 0, 1, up here I get negative 4, and down here I get 1. So I get negative 4 for the derivative, my bad. And then delta x is just 3 the whole time. So I get 1 minus 12 is negative 11. Okay? So then, I'll go up a little bit. And now I want f, so I get negative 11 here. It's really approximately. Okay. So then when I want to do f of x sub 2, well, that's just going to all increment. So this is now f of x sub 1, which is negative 11. Plus delta x, which is still 3. I did these out of order. I realized that. And then f prime of x sub 1. Well, x sub 1, or the point at x sub 1, it's really the whole point, is really 3. So this really represents 3 comma negative 11, right? This one represented 0, 1. So I'm going to sub those in here. So if I plug in 3, I get 3m. And then if I plug in negative 11 here, I get positive 44. Over, if I plug in 3 here, I get 4. And that whole thing we know has to equal 21. All right, so that's what we have to solve. All right, so we are just going to add 11 to this side. So I'm going to go up here. I'm running out of room here. I'm going to add 11 here. So I'm going to get 3, and then I have 3m plus 44 over 4 equals, if I add 11, I get 32. And then I'm going to divide by 3 and multiply by 4. So I'm going to get rid of this 4 by multiply by 4 first. So 4 times 32 is 128, and then over 3. So I get 3m plus 44 is equal to 128 over 3. And then I'm going to subtract 44. This one, the algebra in it is just kind of ridiculous. But so 128 over 3 minus 44. Well, 44 times 3 is 132 over 3. So I end up getting negative 4 over 3. And finally, when I divide by 3, I get negative 4/9, which is D. That one is a doozy. So you just have to understand, like, using this recursive process for Euler's method. Sub in f of x sub something plus delta x times f prime of that same. And this one is really supposed to be like x naught, y naught. It's supposed to be both. So I can fix that. That's really x naught, y naught. And then it increments to x1, y1 when we get to here. Okay. But the answer is definitely D. All right. Here we have integration by parts. I am going to do tabular integration. I'm a fan of that whenever you have a power of x times cosine or sine. So I do my u dv columns, and my u is x, and my dv is cosine 3x. And then what I do is I derive this until I get to 0, and then I take the antiderivative of this, so that's 1/3 sine 3x, and then I do it again, and that's negative 1/9 cosine 3x. And then I go boom, boom, and I do plus minus. So my antiderivative is 1/3 x sine 3x, that's this, minus negative, so I get plus 1/9 cosine 3x, and that's evaluated now from 0 to pi. So I'm going to go down here. When I sub in pi, sine of 3 pi, which is still pi, that's 0, and cosine of 3 pi is negative 1, so I get negative 1/9 for this whole thing when I plug in pi. Now 0, sine of 0 is 0. Cosine of 0 is 1. So I get 1/9, but I got to remember I'm subtracting 1/9 because it's f of b minus f of a is the fundamental theorem of calculus. So then I get negative 2/9, which is answer choice A. All right, let's keep going. So we have number 17 here. And we have the rate at which the boxes are filled. Use trapezoidal sum in the table to approximate the number of boxes filled in the first 14 days. So that is just going to be the integral from 0 to 14. Yeah, the first 14 days, but they're not giving us 0, but that's fine. Yeah, during the first of b of x, because that's a rate dx. So this is what we're approximating, okay? So we're going to use trapezoidal rule. So the first one, we're going to use this. So we have to actually do it because they're not even intervals. So we have to do the area of a trapezoid each time. So the area of a trapezoid is the average of the bases. So the bases here are really the heights, because it's like, these are really like sideways trapezoids, all right? So like this is like, the 180 or backwards, but this is like the 100 and that's the 80. So we're doing 100 plus 80 over 2. That's the average of the bases times the height. The height is really going this way, but that's really delta x. So that's 2. And then I just do this for each one. So the next one is 6 times 80 plus 40 over 2. And then the next one is 1 times 40 plus 50 over 2. And then finally the last one is 4. I'm going to run out here. And then that's 50 plus 70 over 2. And then it's just about simplifying. So the 2's cancel, so I get 160. Cancel, so they get 160. This becomes 3 times 120, so I get 360. Here I get 90 over 2, which is 45. And this one I get 124 divided by 2 is 2. So then I get 240. I did that really quickly. And then when I add those up, you end up getting C 825. All right, so the integral of boxes per day is going to give us boxes. So that'll be the the total number of boxes that were filled during the first 14 days. And then you just got to know, you can't memorize the trapezoidal rule and how that is like, has like a 1/2 delta x that they factor out, and then you just like add like the first height and then 2 of the next and 2 of the next and 2 of the next and 1 of the last. You can't just memorize that. You got to know where it comes from, and you have to know how to find individual trapezoids for a problem like this when we have uneven intervals or uneven subintervals. Okay. So the convergent power series has a sum equal to that. So which one works? So the way that we want to do this is realize that pretty much the exception to this is a telescoping series, but put that aside. If they are giving you the sum of something, then it's going to be geometric, all right? And what we want to do is kind of just look at groups of them. So I'm going to look at these two first. I'm going to kind of check them. And I'm going to rewrite what we're taking the summation of as this. I'm going to say that this is x to the 3n times x cubed over 2 to the n. And then that's the same as, let me think about that. That's the same as x cubed, so that's this. And then this is x cubed to the n, this one, over 2 to the n. And then that all ends up being x cubed times x cubed over 2 all to the n. Okay, so that, I want it to look geometric. Right? So that tells me that this is our common ratio. So remember, our formula is A over 1 minus R. So that's our common ratio on the bottom. And then our A is our first term. Well, here, these are all starting at 0. So anything to the 0, so this is our first term. So checking both of these, this is what the summation would give us. And then when we simplify this, we multiply everything by 2, and we get 2x cubed over 2 minus x cubed, which so doesn't really give me this, but it does for A, because then I'm multiplying A by 1/2. So B is wrong, but if I multiply this by 1/2, all right, that cancels this too, and I do get this. So A is our answer. If that didn't work, I would rewrite these. These I'd have to do individually, so I would just choose one of them. And then I'd be down. If that one didn't work, I would know I had the other one. All right, so this one is just about rewriting it in terms of geometric, using this formula to see which one actually gives us that. And I chose A and B because I could check those two like at the same time. You really got to kind of check each answer. It's really the way that this is set up. All right. Let's keep this moving and take a look at number 19. So we have the slope of the tangent line when a equals root 2. So I'm just going to plug them in. I don't know why. You just make it as do extra work here. So if I plug in root 2 squared is 2. So I get minus 4 xy equals 1. All right. So I'm going to take the derivative using implicit differentiation. So I got 2 x cubed plus y to the first times the derivative of x cubed plus y, which is 3x squared plus dy dx, and then minus product rule. So 4 derivative of x is 1y, minus, distribute the negative in your product rule, and you get minus 4x dy dx equals 0. And then what we're going to do is we're going to plug in the point now. All right, don't waste your time rearranging, plug in the point now. So if x becomes 0, then this is 0, this is 1, so that's 2. And then this becomes 0, so that's dy dx. I don't know why I wrote parentheses. And then minus, if this is a 1, that's 4. And then this is 0, so it goes away. So boom, just like that, we end up with dy dx. If I add the 4 and divide by 2, I get 2. So the answer is C. All right, so the takeaway here is when you're doing implicit differentiation, if you are finding the derivative or the slope at a specific point, just plug in the point right away when you after you take the derivative, and then the algebra becomes a lot easier rather than having to like FOIL and distribute the two and do all that work to get dy dx by itself to then plug in the point and get the same answer. All right, a circle is inscribed in a square. And the area of the circle is increasing at a rate of something. And as the circle expands, the square expands too. At what rate is the area of the square increasing? So the key here is that we have r here. All right, so we have, we'll call it area of the circle is pi r squared. And then if I want to find the area of the square, well, this is going to be 2r, and if I square that, I get 4r squared. So here I have my two formulas, all right? And what I want to do is the only information I'm giving is the area, the rate at which that's changing. So I have dAc dt is 2 pi r dr dt, all right? So I have that, but I don't know dr, and I don't know r. So that's kind of interesting, right? But I do know that this is 15 pi. So 15 pi is equal to 2 pi r dr dt. Pi's cancel. So I know that r, I should have went down there, but I'm going to go over here. So I have 15 over 2 is r dr dt. That's really all I can do here. They don't tell me r or dr dt. So then just put that on hold, have faith, and then take the derivative here. So now I get dAs dt, all right, the rate at which the area is changing, that's what we're looking for, is 8r dr dt. Oh, there we go. So r dr dt together is 15 over 2. So I get 8 times 15 over 2, and 8 divided by 2 is 4, and 4 times 15 is 60. So I just get 60. So the answer is D. All right, so you solve the first one as far as you can go, and then just put that on hold, go and do the other one, which is what we're looking for, and then again, have faith that it's going to work out. Someone designed this problem to work out, so you just got to keep powering through in a way. All right, so we've got this region bounded by polar curves, and in the first quadrant, what is the area of S in terms of C? Okay, so what we have to know is what we're doing is the area of this polar curve, we are doing 1/2 times the integral. So this is just how you always integrate a polar curve. It's 1/2 the integral of r squared. Well, r is 2 theta, and 2 theta squared is 4 theta squared d theta. And then usually the hardest part is knowing what we're integrating between, or the limits of integration. So if I think about how I'm kind of looking at this curve, how I'm sweeping it out, I'm clearly starting at 0, because if I start here, 2 times 0 is 0. And then I'm integrating until I get to an angle of C, right? I'm stopping at angle C. And that's it. I'm just going to now do this. Again, it seems a little weird, but just keep going. Do what you normally do. When you get to a place where you're a little confused, just think what you do in an easier problem. In like a school problem, typically, you're just going to have like the integral from 0 to 5, or probably like pi over 2 or something like that. But you just find the antiderivative. So 1/2, the antiderivative of 4 theta squared is 4 theta cubed over 3. And I'm going to integrate that like normal from 0 now to C, okay? So when I plug in C, I get 1/2 of 4/3 is 2/3 C cubed, minus when I plug in 0. But when you plug in 0, you just get nothing. So you just get 2C cubed over 3, which is answer choice C. All right. On to number 22. Ooh, we got a lot going on here. So we have a table, and we have h of x, is f of 5 of x, which the following must be true. So what we have to do is be able to kind of read each of these and know what they're referencing. So there exists a c such that h of c is equal to a number. That is IVT. We have to know that language and be like, okay, they're talking about IVT, intermediate value theorem. So how do I know that's true? Well, I am going to plug in h of 1, and I'm going to plug in h of 3. And then I'm going to see what happens, because this is what the intermediate value theorem is saying. Find f of b, find f of a, and then it has to hit every value in between those two if it's differentiable. Or, well, if it's continuous. But this is differentiable, which means it's continuous. So h of 1. Well, h of 1 is f of 5. And f of 5 is 4. And then h of 3 is f of 15, and f of 15 is 13. So sure enough, if it goes from 4 to 13, it's going to go through 10. So that one works. All right, so now we're going to check number 2. Well, the language that's similar to up here, but they're talking about the derivative. That's MVT, or mean value theorem. That's the f of b minus f of a over b minus a. So now we want h of 3 minus h of 0 over 3 minus 0. And if it's differentiable, 3 minus 0. If it's differentiable and continuous on that interval, then the mean value theorem is going to say that somewhere the derivative is equal to this value. Well, let's see if we get 4. H of 3 we already found to be 13. H of 0 is f of 0, so that's 1. And sure enough, 13 minus 1 is 12 over 3 is 4. We do get 4. So that works. Well, that doesn't really help me. So honestly, test-wise, I should not have checked number 2 because that was in both answers. I should have jumped to 3 to save time. But in the spirit of going over the problems, I mean, I made a mistake test-wise, but it's still good that we talked about that. I was just so focused. I was in teacher mode there. I was so focused on I want to make sure we talk about mean value theorem. Okay, so now increasing, h is increasing from 2 to 3. Well, h of 2 is really f of 10. And h of 3, we've already talked about, is really f of 15. This is interesting, right? So the derivative seems like it's positive, so it's increasing. And it goes from 8 to 13, so it increases. But these are just select values. We don't know what happened. For all we know, at f of 11, its derivative is negative. And this goes from 8 down to 2 and then back up to 13. We don't know that, all right? We just don't have enough information to say that it is increasing the whole time. So the answer ends up being B. All right. We are moving on to number 23. So we have a power series expansion. So what I'm going to do is I am going to find these individually. All right. So what I do know is we really have to have this part down, what e to the x is. And I'm going to stop there, okay? Because, obviously it keeps going. So technically plus ... And then I'm going to use this to find these two, all right? So I'm going to use it to find e to the 2x first, which means I just replace each x with 2x. 2x squared is 4x squared. I'm not going to simplify, though. That's kind of an important thing. And when I cube 2x, I get 8x cubed over 3 factorial. Okay, so I'm going to kind of hold that. Then I'm going to take this and I'm going to find e to the negative x, which is just 1. I'm replacing each x with negative x. Negative x squared is still x squared. And then I'm going to have minus x cubed over 3 factorial, and then ... I'm in the way here. Can't do the ... Okay. Oh, well. So then that tells me that if I want to multiply all those by 2, 2e to the negative x is 2 minus 2x plus the 2's cancel here, x squared minus 2x cubed over 3 factorial. I don't know if that was a good idea to cancel the 2 out. Okay, but either way. So then I'm going to hold on to that. And now what I'm going to do is I'm going to stop there and then figure out the answer. So what I'm doing is I'm adding these two together, then dividing by 4. So term by term. 1 plus 2 is 3, and 3 divided by 4 is 3/4. Oh no, they all have 3/4, so I just wasted time there. All right, then I'm going to do the next one. So the next one is 2x minus 2x. Okay, well then that goes away. So I'm going to go to the next one. And you know what? I did make a mistake. I didn't make a mistake. I just shouldn't. I should have known better. Don't simplify these. All right, this is really this. Right, because I just multiplied by 2. That's going to be easier to add to this. So 2x squared over 2 plus x squared over 2 is 3x squared over 2. All right, and then I'm dividing by 4. So I'm really getting 3x squared over, sorry, I lost track of that. 3x squared over 4, so that's 3x squared over 16, all right? But it's positive. So this one is wrong. This is 3x squared over 16, so that one's still in. This one's minus, so that one's wrong. Now this one, so this is where, you know, they had 6x squared over 8. Wait, I think I made, let me go back. Oh, I was at, okay. My apologies, but I'm just going to leave this in. I'm not going to edit this. I boxed these in for a reason, and then I used the original. Okay, let's just restart that. Add these two together and divide by 4. Every answer has that. Add these together and divide by 4. 0, gone. Add this plus this. Okay? 4x squared plus 2x squared is 6x squared over 2 divided by 4 is 6x squared over 8. Okay. It's positive. These answers are wrong. Okay? This is 3x squared over 16. That's wrong. This is 6x squared over 8. That's right. Okay, so don't mind me. I've been doing a lot of problems here and recording all of it straight through. So I am having some like fatigue in my mental state here. Okay, so add the idea is create this from e to the x, create this from e to the x, add them together and divide by 4, do it term by term, and then figure out which one matches that. And just kind of eliminate answers. All right, time to regroup. Now, number 24. We've got this interval given that, all right, so we were given some things. What is the integral from 3 to 4? Okay, so what we know is that the integral from 0 to 1 of, and this is v of t that we're looking at, is negative 0.5. So that means this area here, the area is 0.5, okay? But because it's below the x-axis, that's negative. But I'm going to leave it like that. And our goal, let me move this up a little bit, is to find, I'm actually going to move myself for this problem. Our goal is to find the area from here. Question mark. Okay. And then it says that the particles just from 0 to 4, and like this we also don't know as well. So I'm going to call that A. So let's just do this. Let's call that A and that B, and we're looking for B. And then let me call this negative. Okay, now we're all set up. So if the particle's displacement is negative 1, that means negative 0.5 plus A plus B is equal to negative 1. All right, because Displacement is just the total integral, so we're just adding everything. This means that a plus b is equal to negative 0.5. So I have that equation. Okay. All right. Now what I'm going to do is I'm going to look at the total distance. The total distance is just the absolute value of everything. All right. So that is the absolute value of negative 0.5 is 0.5. A stays, but B I have to make negative because it is negative. So I need to make it positive. And that should add up to 3. So now I get A minus B is equal to 3 minus 0.5 is 2.5. Okay? So now I have this and this. I would rather find B. So I'm actually going to negate this one. So the first one I'm going to write A plus B equals negative 0.5. This one I'm going to do negative A plus B is equal to negative 2.5. Add them together. A's cancel. 2B is equal to negative 3. So B is equal to negative 1.5, which is this. And that is answer choice B. Okay. This one was cut off, but it just wanted the, I think it just wanted dy dx. So it wanted dy dx. Whoops, I just wanted dy dx evaluated at t equals 1. All right, so apologize for that. It was cut off. We can't see it. But that's what it was asking for. All right, so if it wants dy dx, dy dx is dy dt over dx dt. So dy dx is simply just 4t cubed minus 5 over 12t cubed minus 8t. And we're just evaluating at 1. So this one's pretty straightforward. Throw in 1 here and you get negative 1. Throw in 1 here and... oh, it's 4t. This is 4t. I did the derivative wrong. Okay, now you plug in 1 here and you get 8, and the answer is B. Negative 1/8. I'm going to move myself back over here. Okay. Number 26. So when we have the integral from 1 to infinity of something that looks like a p-series, I mean, basically is a p-series, right? The rules are the same for converging and diverging as like the summation of a p-series, okay? It has to do with like the integral test. But we don't have to do all of that. All we have to do is a p-series is going to converge when this value is greater than 1. That's all we got to do. Whoops, so 2p is greater than, subtract 3, negative 2. So p has to be greater than negative 1. And if p is greater than negative 1, then this will converge. All right, so you just have to know that when you have the summation of a p-series, it's usually like n. P converges when p is greater than 1. Sorry, the whole thing converges when p is greater than 1, diverges when it's less than or equal to 1. That same thing holds true when you have the integral from 1 to infinity of 1 over x to the p. And they're using p here, but I'm just using it what it normally is. All right, so whatever thing is in the position of p just has to be greater than 1. All right, 27. What are the first 5 non-zero terms of the Maclaurin series for G? So the way that I'm going to do this is I am going to try to build it from something that I know already. So I'm going to start with the fact that cosine x this is one we just need to know, is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and on and on and on. Okay, so the way that I'm going to do this, and then I want to do something with x to the 4th. So I'm just going to sub in x to the 4th. So that means I get 1 minus, this becomes x to the 8th over 2 factorial. Then this becomes x to the 16th over 4 factorial. And then this becomes x to the 24th over 6 factorial, and then on and on and on. I probably don't even need that much, right? But I'm just replacing each x with x to the 4th. Now, this is g prime. All right? And it wants the first 4 non-zero terms of g, which is the antiderivative of this. All right? So that tells me that I just need to find the antiderivative of this. And then I'm going to have a plus c at the end of it, which I'm going to write first, and that's just this. So, but this doesn't really help me. All the answers have a 5 in it, okay? So then the antiderivative of 1 is x, all right? So that gets rid of b. I'm just going to keep going until I have my answer. And then I'm taking the antiderivative of this. This is x to the 9th over 9 times 2 factorial. So now I'm done. These went the wrong way, so now I have a. So again, we're trying to do the least amount of work here to figure it out. All right, so we start with cosine. You don't ever want to do like the Taylor series the long way unless you like it's a different type of problem. But when it's cosine, sine, that's why you have to know those foundational, really Maclaurin series, and then build off of those. So don't worry about the derivative yet. Just start with cosine, get cosine to the 4th. If they have the derivative and they're looking for g, you just integrate term by term and throw the constant in the front. And then just figure out which one actually matches. All right, we are getting close to the end here. 3 problems left. Let's see if I can make it. We are given a function, and we want to know which of the following must be true. Must be true, okay? Well, it would be easy to answer these if I knew what the actual function is. And we can figure that out, but we do not want to do the actual limit of this. Notice that this is the derivative, all right? I mean, I'm telling you, f prime of x, but this is the definition of the derivative. So all we have to do is just extract the actual function from that. So we just need to know what f of x is, all right? So remember, the f prime of x is, the limit as h approaches 0, of f of x plus h minus f of x. Well, f of x is just here. So f of x is just x cubed. And then they're asking us questions about f prime. Well, f prime of x is 3x squared. Okay. Well, is f prime of x always less than 0? No, that doesn't seem to make sense because x squared is always positive. So f prime of x is always greater than 0. So that's true, and that's not. And then f of x is concave down when x is greater than 0. We could look at that 2 different ways. We could just know what x cubed looks like, and that's certainly concave up. So that one's wrong. So it's B. Or if we didn't know what that looked like, which we definitely should, we could take the second derivative. We get 6x. And when x is greater than 0, this is positive, so then the original would be concave up. But if you should know what x cubed looks like, so you don't have to worry about taking the second derivative. All right, on to our last 2 problems of the non-calculator section. This one we get a pretty straightforward problem here. We're doing the derivative of a quotient evaluated at a number, so just do the quotient rule. And they're actually using f and g, so just like literally copy the quotient rule, f prime g minus g prime f all over g squared. And then we're evaluating each of those at 3. So f prime of 3 is negative 4. G of 3 is negative 9. Minus g prime of 3 is 6. And f of 3 is 7. All over g squared. Well, g of 3 is negative 9. And negative 9 squared is 81. So then I get 36 minus 42 is negative 6 over 81, and negative 6 over 81 divided by 3 gives you b. All right, so at the end here, second to last problem, we get kind of a more straightforward problem. Just know the quotient rule and just apply it with the table. All right, let's do our last problem of the section. So, we got the second derivative graph. They're giving us some values of the derivative. So this is how we want to do it. We want to use the second fundamental theorem of calculus. We're going to integrate from 0 to 2 of f double prime of x dx. And then just using the second fundamental theorem of calculus, just think about how you do that. First step, find the antiderivative. The antiderivative of f double prime is f prime. Then sub in 2 and 0 and subtract them. So f prime of 2 minus f prime of 0. A problem like this is either going to be you're going to know the function and you're going to not be able to do it because it's too complicated, and then on a calculator problem you would use Desmos to solve it. But on a non-calculator, we need to know this represents the area. So the integral from 0 to 2 of the f double prime graph is just the area of this triangle. This is a base of 2. This is a height of 8. 2 times 8 is 16 divided by 2. It brings us back to 8. So the integral from 0 to 2 is 8 because it's the area over here. F prime of 2 is unknown. That's what they're asking us about. F prime of 0 is 3.6, and now I just add it over. So 11.6 is f prime of 2. So therefore, that is answer choice C. And that takes us to the end. So thanks for watching. There will be another video that you can check out where I will do the same thing for the calculator questions. But I need a little break here mentally, and then hopefully I'll regroup. So hopefully you stayed and watched the whole thing, or you kind of like skipped through and looked at the problems that you wanted to. But in the end, all the answers are correct. A couple of the questions I made silly mistakes on. But hopefully that helped just watching me kind of go through the problems. And you can kind of see how you want to approach these problems, these non-calculator multiple choice. All right, so check out the other video where I go through the multiple choice with calculator and kind of show you some like Desmos tricks as well along the way. All right, hope that helped.